Class 11th Chemistry, Unit 6 Thermodynamics, and in this video we will discuss about enthalpy and relation between delta U and delta H. First of all, enthalpy, which is represented as H. The heat absorbed at constant volume is equal to change in internal energy. That is, delta U is equal to QV. This relationship we have discussed in the previous video. But most of chemical reactions are carried out not at constant volume, but in flasks or test tubes under constant atmospheric pressure. That's why another thermodynamic function is introduced, and that function is known as enthalpy. Okay, represented as H. Greek word enthalpion means to warm or heat content, and this enthalpy is given as H is equal to U plus PV. It means enthalpy is the sum of internal energy and product of pressure volume. Enthalpy is a state function. It means depends on initial and final states of the system. And we already discussed that this absolute value of this U cannot be determined. That's why absolute value of H also cannot be determined. But we can determine the change in enthalpy, that is delta H, and which is given as delta H is equal to H2 minus H1, where H1 is the enthalpy in state 1 and H2 is the enthalpy in state 2. Okay. Mathematical statement of the first law of thermodynamics is delta U is equal to Q plus W, and where this W is the work and the pressure volume work is given as W is equal to minus P delta V. If we combine these two equations at constant pressure, then we will get delta U is equal to QP minus P delta V, where this QP is heat absorbed by the system and this minus P delta V is the expansion work done by the system. Okay, let us consider two states, state 1 and state 2. In state 1, internal energy is U1, and in state 2, internal energy is U2. In state 1, volume is V1, and in state 2, volume is V2. Then change in internal energy can be given. U2 minus U1 is equal to QP minus P V2 minus V1. This is from this relationship. Okay, delta U, this is change, that is U2 minus U1, and here this is delta V, this is again change in volume, that's why this is V2 minus V1. Now if we rearrange this equation, how you can write this can be written as U2 minus, this is U1, this is equal to, this is QP, and just open this bracket, we will get P V2, and this is minus minus plus, this is P V1. Okay, then we can write this is QP, this is equal to, this is U2, okay, U2, and this will be written as plus, this is P V2, this is minus, this is U1, and this is minus P V1. Okay, now these terms can be written like this: QP is equal to U2 plus PV2. Okay, then from these two, if we take the minus common, then we can write U1 plus PV1. Okay, now just compare this relationship with this. H is equal to U plus PV. Then this term U2 plus PV2 can be written as H2, and this U1 plus PV1 can be written as H1. Okay, now put these two values in this equation, then we will get QP is equal to H2 minus H1, and this is equal to delta H. That's why we can say this is change in enthalpy is the heat absorbed by the system at constant pressure. Okay. For finite changes at constant pressure, the equation H is equal to U plus PV can be written as delta H, that is change in enthalpy, is equal to delta U plus delta PV. This we can write like this. Okay, since pressure is constant, that's why this relationship can be written like this. Delta H is equal to delta U plus P delta V. Okay, remember this. Delta H is equal to QP, and this is heat absorbed by the system at constant pressure. Delta H is negative for exothermic reactions which evolve heat during the reaction, and delta H is positive for endothermic reactions which absorb heat from the surroundings. At constant volume, it means when delta V is equal to 0, we can write delta U is equal to QV. Okay, then from this relationship, when this delta V is equal to 0, then we can say delta H is equal to delta U. Clear? Change in enthalpy is equal to change in internal energy. As we know, delta H can be written as QP and delta U is written as QV, and both are equal. That's why we can write this one. Delta H is equal to QP, which is equal to delta U, and that is equal to QV at constant volume. The difference between delta H and delta U is not usually significant for systems containing of only solids and or liquids. Why? Because solids and liquids do not suffer any significant volume change upon heating. But if gases are involved, then this relationship between delta H and delta U is important. Relation between delta H and delta U for the system having gases. Let us consider a reaction involving gases. If VA is the total volume of the gaseous reactants and VB is the total volume of the gaseous products, and in the same way NA is the number of moles of gaseous reactants and NB is the number of moles of gaseous products, then at constant temperature and pressure, using ideal gas equation PV is equal to nRT, we can write PVA is equal to nART and PVB is equal to nBRT, and then PVB minus PVA, this is equal to nBRT minus nART, and this RT is common. That's why we can write this is equal to nB minus nART. Now, in this P is common. That's why P is equal to VB minus VA, and this is equal to nB minus nART. Where this VB minus VA, this is the change in volume, that is equal to delta V. That's why P delta V is equal to delta nGRT. Now what is this delta Ng? This refers to the number of moles of gaseous products, that is NB, minus the number of moles of gaseous reactants, that is Na. Okay. And from this delta H is equal to delta U plus P delta V. If we put the value of P delta V, which is equal to delta NGRT, we will get this relationship. This is one important relationship. and some numericals may be asked based on this relationship. Delta H is equal to delta U plus delta N GRT, where this G refer the for gaseous substances. Okay, let us see one question. Problem 6.5. If water vapor is assumed to be a perfect gas, molar enthalpy change for vaporization of 1 mole of water at 1 bar and 100 degrees Celsius is 41 kilojoule per mole. Okay, that is enthalpy change for vaporization. Simply we can say change in enthalpy is given. Calculate the internal energy change, that is delta U, when 1 mole of water is vaporized at 1 bar pressure at 100 degrees Celsius. For this change, we can write the equation. H2O liquid is converting into H2O gas, and this is the relationship between delta H and delta U. Delta H is equal to delta U plus delta Ng RT. We have to find out delta U. That's why you can write delta U is equal to delta H minus delta Ng RT, where this delta H is given 41 kilojoule per mole. Delta N gas is equal to 1. Now what is this delta N gas? This is the number of gaseous moles in product side minus number of gaseous moles in reactant side. Now in this question, product side there is a 1 mole of H2O in product side. That's why 1 minus, and in the reactant side no gaseous mole is there. That's why 1 minus 0 is equal to 1. That's why this is delta Ng is equal to 1. Value of R, gas constant, 8.3 joule per Kelvin per mole. Convert this into kilojoule. That's why we multiplied by 10 to the power minus 3. Why we are converting this into kilojoule? Because this delta H is given in kilojoule. Temperature is given in 100 degrees Celsius. Convert this into Kelvin, and that is equal to 373 Kelvin. Now put the value. Delta U is equal to 41 kilojoule per mole minus 1 into 8.3 into 10 to the power minus 3 kilojoule per Kelvin per mole into 373. And then this is 41 kilojoule per mole minus 3.096 kilojoule per mole. And if you solve it, you will get this one. Delta U is equal to 37.904 kilojoule per mole. Okay. Thank you. Subscribe my channel to get the new videos from this chapter.